Imagine for a second that you go out and you buy a state-of-the-art, top-of-the-line appliance for your home.
Like a massive smart refrigerator or something.
Right, exactly.
Yeah.
Or maybe one of those ultra-high-definition wall-sized televisions. You unbox it, you plug it into the wall, it turns on, and it does exactly what you expect it to do.
The food gets cold, the movie looks great.
Yeah, but what you don't know, and well, what you literally can't see, is that because of the specific way it was wired into your house, this brand new machine is secretly siphoning an extra $40, $50, maybe even $100 out of your bank account every single month.
Ouch.
Yeah.
Just bleeding you dry.
Quietly bleeding you dry year after year. And you're totally oblivious because, I mean, when you push the button, the machine turns on.
It's the perfect invisible crime, really. You get the immediate result you wanted, so you have absolutely no reason to question the invisible processes happening, behind the drywall or out in the yard.
And that invisible crime is basically the core of our deep dive today. We're looking at the hidden financial drain of bad HVAC installations, specifically focusing on heat pumps.
That's a huge issue.
It really is. And we have a fascinating stack of sources for this one to help us really understand the stakes. We're drawing on the extensive field observations of Dave Hartzell. He's a 45-year veteran HVAC expert operating out of Oklahoma.
Right, lots of extreme weather experience there.
Definitely. And we're pairing his real-world boots-on-the-ground experience with a heavy-hitting 2016 federal research document. It's called NIST Technical Note 1848. For those who aren't familiar, NIST is the National Institute of Standards and Technology.
Which means they are the people who literally define the exact measurements of our physical world in the U.S. They maintain the atomic clock.
Wow. Okay, so they don't mess around.
They do not. So when NIST decides to do a study on air conditioning efficiency, they aren't just, running a few computer simulations or guessing based on theory.
Right.
They're building highly controlled environmental chambers to simulate extreme weather. And then they're measuring electrical drawdown to the exact watt just to see exactly how these machines fail under pressure.
So our mission today is to help you, the listener, understand why HVAC installation quality isn't just some, technical checkbox for a contractor to tick off before they leave your house. It is a literal, measurable, and often massive tax on your monthly utility bill.
A completely avoidable tax, too.
Okay, let's unpack this, because reading through this NIST data, I kept thinking about buying a highly rated, wildly expensive sports car, but driving it off the dealership lot with flat tires.
Yeah, that's exactly what it's like.
Right. All those high-end engineering specs under the hood, the aerodynamics, the horsepower ratings, they mean absolutely nothing if the fundamental setup connecting that vehicle to the ground is flawed from day one.
The machine can only perform as well as the environment it's installed into. But before we get into the specific flats on those tires, we need to talk about the underlying mechanics.
Okay, lay it on me.
We need to understand why NIST focused so intensely on heat pumps for this research, rather than, say, traditional air conditioners or gas furnaces.
Yeah, the source material points out a really stark contrast here. If you have a traditional gas furnace and it has an installation problem, say, the airflow is a bit restricted or something, it's going to run inefficiently, right?
It'll wear out components faster.
But at the end of the day, a furnace is essentially just fire in a box. It burns a fuel, it gets hot, and it blows that heat into your living room. It will still eventually heat your house.
Exactly. A gas furnace brute forces its way to the finish line. The relationship between its fuel and its heat output is fairly linear. But a heat pump operates on an entirely different plane of physics.
Because it doesn't actually create heat, right?
Right. It moves heat from one place to another using the refrigeration cycle. It relies on manipulating the pressure of a chemical refrigerant so that it changes phases from a liquid to a gas and back again.
Okay, so gas absorbs, liquid releases.
You got it. When it turns into a gas, it absorbs heat. When the compressor squeezes it back into a high-pressure liquid, it releases that heat.
So it's not brute force at all. It's an incredibly delicate balance of pressure, chemistry, and airflow all happening simultaneously.
Exactly. Because it relies on those phase changes happening at very precise temperatures, an installation fault on a heat pump doesn't just cause a linear drop in efficiency.
It crashes.
It collapses exponentially. If the pressure is off, the chemical doesn't boil at the right temperature, the heat isn't absorbed, and the entire transfer mechanism just falls apart.
Right.
The worse the installation fault, the faster the machine's ability to do its job collapses on itself.
And we have to factor in the environment, too. I mean, Dave Hartzell, the veteran HVAC tech from our sources, he operates in Oklahoma.
Oh, yeah, brutal extremes.
You're dealing with blazing 100-degree summers where the system runs all day long and freezing winters where the heat pump has to carry the heating load before the incredibly expensive emergency auxiliary heat strips kick in.
Which you really don't want running if you can help it.
Right. So what does this all mean for the average homeowner? Are we talking about a slight dip in performance or total system failure?
Total system failure is a very real possibility, especially when the weather hits those extremes. And that is exactly what the NIST researchers wanted to quantify.
They wanted to find the breaking point.
Exactly. They wanted to know where that breaking point was and, more importantly, how much it costs the homeowner before the machine finally breaks.
So what did they do?
In their lab, they took physical heat pumps and intentionally broke the installation process in highly specific, measurable ways. They didn't just guess. They built laboratory test rigs to simulate these faults in isolation and in combination.
To measure the exact drops in performance.
Right. They tracked two key metrics. The first is COP, the coefficient of performance, which is basically asking for every unit of electricity we put in during the winter, how many units of heat do we get out?
Makes sense. And the second?
The second is ER, the energy efficiency ratio, which measures the cooling efficiency in the summer.
Got it. So let's look at the first specific installation fault they tested, which takes us deep inside the chemical loop of the machine, the refrigerant charge.
The literal lifeblood of the system.
Yeah. And they tested two scenarios here, undercharging and overcharging the system with refrigerant. Let's talk about undercharging first, because the sheer financial gravity of this is staggering.
It really is.
According to the NIST data, if a heat pump is undercharged by just 20%, it loses roughly 10 to 15% of its heating efficiency.
And a 10 to 12% cooling loss in the summer.
Right. And if that undercharge pushes to 30%, which the sources say is surprisingly common out in the field, you lose over 20% of your heating efficiency right out of the gate.
Which is massive.
Let's translate those percentages into actual dollars for you listening right now, because percentages can feel a bit abstract until you look at your bank statement.
Very true.
Say you have a summer AC bill of $150 a month. If you have a 10% efficiency loss, simply because the technician didn't put enough refrigerant in the machine, that is $15 a month just evaporating into thin air.
Gone.
Over a 6-month cooling season, you just lost $90. And that compounds year after year after year for the life of the unit.
And that is just the utility bill. There is a massive unseen cost happening inside the machine itself.
Because it's working harder, right?
Exactly. Because there isn't enough refrigerant to carry the heat, your compressor, which is the incredibly expensive engine of the whole system, has to work overtime. It has to run longer cycles to move the same amount of heat, which drastically shortens its lifespan.
What's fascinating here is, wait, you mentioned the dichotomy earlier.
Yeah, what's fascinating here is that dichotomy. Yeah. Undercharging is a silent, compounding financial leak that slowly shortens equipment life, while overcharging is a sudden catastrophic failure waiting to happen.
So let's talk about that flip side, overcharging. The sources note this is less common, but it frequently happens when a technician arrives at a house, assumes the system is low without doing the proper math, and just blindly adds refrigerant to, top it off.
Which you should never do.
Right. And while undercharging is a slow leak, overcharging causes elevated head pressure inside the system.
Yeah, and if a system is severely overcharged, you run the risk of something called liquid slugging.
Liquid slugging sounds bad.
It is very bad.
Yeah.
We have to remember that compressors are designed specifically to compress a gas. But when you overfill the system, liquid refrigerant can make its way back into the compressor.
And you cannot compress a liquid.
You cannot.
I was trying to wrap my head around the physics of this to understand why it's so destructive. Overcharging a system isn't like, giving an engine extra high-octane fuel to make it run faster.
No, not at all.
It's more like trying to close a heavy steel vault door when there is a solid brick sitting in the door frame.
Oh, that's a great way to picture it.
Yeah, like the door is the mechanical piston inside your compressor, and the liquid refrigerant is the brick. It doesn't give you more energy. If the motor forces that door shut against an immovable object, it just makes the whole system sick, sluggish, and prone to breaking down. The mechanical piston shatters. Boom. Catastrophic compressor failure.
That is a perfect visualization of liquid slugging. The system literally destroys itself trying to compress the uncompressible.
So that covers the chemical side of the equation, the refrigerant loop.
Right, but the heat pump relies on two loops functioning in perfect harmony. The chemical loop, absorbing the heat, and the mechanical air loop delivering the heat.
So you can have the chemical mix perfectly balanced, but it's useless if there's no air moving over it.
Exactly. The mechanical side has to deliver. And the sources detail a few common culprits that completely choke off this air loop.
Like what?
A huge one is undersized ductwork left over from the 1970s and 80s. A contractor will come in and slap a brand new high-capacity air handler onto those old, tiny ducts. The system is trying to push massive volumes of air through the equivalent of a cocktail straw. That creates high static pressure, which is just a fancy way of saying resistance to airflow.
And you've got other issues too, right? Like filters.
Yeah, heavily restricted, Heimer filters that homeowners just forget to change, and dirty evaporator coils that act like a clogged artery, getting worse every single season.
The NIST findings on airflow are incredibly precise here. A 20% reduction in airflow drops your efficiency by roughly 10% in both heating and cooling modes.
But NIST didn't stop there. They didn't just test these faults in isolation. They wanted to know what happens when these incredibly common errors happen at the same time.
Here's where it gets really interesting, because looking at the data, the math isn't mathing for me.
What do you mean?
Well, if I have a 10% efficiency loss from low airflow and a 10% loss from an undercharge, why doesn't that just equal a 20% loss overall? Why are the numbers so much higher when they're combined?
Because the efficiency losses are not additive. They are multiplicative. They interact to create a much larger combined loss.
Can you break that down?
Sure. Think about the underlying mechanism we talked about earlier. The system needs air moving over the indoor coil to deliver heat to the chemical refrigerant. If you have low airflow, very little heat is being delivered to the coil.
Okay, I follow.
If you also have a low refrigerant charge, the system doesn't have enough chemical capacity to absorb what little heat is actually making it there. You're starving the coil of heat, and you're starving the system of the chemical needed to move it.
Wow.
These two faults force the compressor completely out of its designed operating parameters. It's fighting physics on two fronts simultaneously.
Right. It's like trying to run a marathon with both asthma, which represents your low airflow, and anemia, which represents your low blood count or low refrigerant. Asthma makes it mechanically hard to get oxygen into your lungs. Anemia means you biologically don't have enough red blood cells to carry whatever oxygen you do get to your muscles. 1 + 1 doesn't equal 2 in that scenario. It equals a total physical collapse on mile 3, because the two conditions are actively amplifying each other's worst effects.
The system compounds its own failures, exactly, which sets up the third major fault NIST tested.
Duct leakage.
Right. We've established the chemical loop is critical and the mechanical air loop is critical. But let's say your contractor did an amazing job on the unit itself.
The dream scenario.
Right. Your refrigerant charge is flawless, your air handler is clean, your filters are fresh, and the air is moving through the indoor machine exactly as it should.
Okay.
What happens if that perfectly conditioned, perfectly balanced air never actually reaches your living room?
We are talking about cooling the attic.
It is maddening when you see the numbers. The research highlights that 20% duct leakage into unconditioned spaces like attics or crawl spaces is incredibly common, especially in older homes.
20%.
Yeah. The old duct tape deteriorates over decades in a hot attic, the mastic sealant cracks and falls off, or maybe the joints were never actually sealed properly in the first place.
The penalty for that is staggering. A massive 15 to 20% efficiency loss, because every cubic foot of cold air that leaks into your 130-degree attic is air you paid a premium energy rate to create, and you get absolutely zero benefit from it inside your house.
None.
The dollars and cents here are wild. According to the data, duct sealing alone can reduce your entire HVAC energy consumption by 15 to 25%.
Which pays for itself so fast.
Literally, if you have a $200 summer electric bill, that's $40 a month. That means paying a professional to go up into your attic and properly seal those ducts literally pays for itself in a single season.
If we connect this to the bigger picture, it highlights this profound absurdity in how we view home maintenance.
What do you mean?
People will drive 10 miles across town to save 5 cents a gallon on gasoline, but they're essentially paying premium utility prices to air condition the dusty attic space where they store their old holiday decorations.
It's exactly like paying your internet provider for a premium gigabit internet package, but leaving your Wi-Fi network completely unsecured and letting your neighbor secretly siphon off 20% of your bandwidth to stream movies all day.
Yes.
You are paying for the capacity, you are doing all the heavy lifting, but someone else, or in this case, the squirrels living in your attic, are enjoying the product.
And this brings all the pieces together into the nightmare scenario. NIST's lab tests weren't just academic exercises in a vacuum. They were simulating the exact reality field technicians like Dave Hartzell see in Oklahoma every single day.
So if I'm putting myself in the shoes of that HVAC tech, I'm walking into a house where the homeowner bought a brand new, highly efficient heat pump maybe 5 years ago,
Right.
but the installer rushed the job and skipped the load calculation. That means I'm looking at a system that is already running a 15% refrigerant undercharge.
Then, the installer never bothered to check the old 1970s ductwork, which is severely undersized for the new, modern blower motor.
So that's a 20% reduction in airflow right there.
Yep. And because no one went into the attic, those same old ducts have cracked seals and are leaking heavily.
Another 15% loss.
Exactly. When you combine all three of those incredibly common, completely invisible faults, NIST's data suggests that brand new state-of-the-art system is operating at maybe 60 to 65% of its rated efficiency.
That is heartbreaking. Let's talk about SEER ratings for a second. SEER stands for Seasonal Energy Efficiency Ratio, and it's basically the miles per gallon rating for your air conditioner.
The higher the SEER, the more efficient the unit.
And the more expensive it is to buy. In this nightmare scenario, you paid top dollar to the manufacturer for a premium 18 SEER efficiency system. But because of the shoddy installation, the math dictates you're only getting 14 SEER performance.
And you're paying that financial difference to the utility company every single month.
But here is the fascinating psychological blind spot in all of this. Most homeowners are completely in the dark.
Oh, totally.
The thermostat clicks, the system turns on, cold air eventually comes out of the vent. When the massive electric bill arrives in the mail in August, they don't blame the heat pump. They just shake their fists at the sky, complain about the weather, and blindly blame rising energy prices.
They never suspect the machine.
No. They're completely unaware their system is actively wasting 40% of the energy it consumes before a single drop of cold air hits their face.
Which is exactly why NIST Technical Note 1848 is such an important document for the industry. Yes, it's a research paper. There's no federal law requiring a local contractor to comply with NIST 1848. But it provides the undeniable, peer-reviewed hard data to justify strict industry standards. It validates protocols like ACCA 5 and ACCA 9, which are the industry's official manuals for quality installation and maintenance.
So what do those manuals actually require?
They mandate that technicians actually take specific scientific measurements. It proves why a proper commissioning audit is absolutely vital when a new system is put in. A technician cannot just turn the unit on, feel cold air, and drive away.
They have to do the math.
Right. They have to measure subcooling, which is testing to see if the liquid refrigerant has cooled down enough before it loops back to absorb more heat to verify the charge is perfect. They have to measure static pressure to verify the ductwork can actually handle the airflow. They have to physically test for duct leakage.
Because installation quality is not an abstract concept. It is a strict financial contract that dictates the true cost of your home comfort for the next 10 to 15 years.
Beautifully said.
An audit with actual measured values is the only way to expose these invisible drains. If your system runs constantly in the summer and your bills are through the roof, it might not just be a hot July. It might be the math.
That hard data, the subcooling numbers, the static pressure readings that is your shield against throwing thousands of dollars into an unsealed attic over the lifespan of the equipment.
Which leaves us with one final, very provocative thought to chew on. At the very end of our source material, there's a tease for an upcoming industry standard called ACCA 12QH, which deals with whole home performance evaluation.
Ah, yes.
And it really got me thinking. We just spent this entire deep dive looking at how 3 invisible flaws in a single machine can rob you of nearly half its value.
It forces you to zoom out and ask, how much invisible waste exists in the broader ecosystem of your entire house.
Right. Between microscopic gaps in your attic insulation, aging double-pane windows that have lost their seals, and thermal bridging pulling heat right through your hall studs. Are we constantly throwing money away to heat and cool the outdoors Simply because we are too focused on buying highly rated, efficient machines rather than building efficient environments for those machines to live in.
That's the real question.
Think back to that sports car with flat tires. Are we spending thousands of dollars constantly upgrading the engine, completely ignoring the fact that the floorboards are rusted through and we're just dragging our feet along the highway? It makes you look at your living room and your utility bill in a completely different light.
The house is a deeply interconnected system.
Yeah.
You can't change one variable without impacting the entire equation.
Definitely something to mull over the next time you hear your AC kick on. Thanks for joining us on this deep dive into the hidden world of HVAC installations. Take a look at your own setup, maybe call a professional to schedule that audit, and whatever you do, stop cooling the attic. We'll catch you on the next one.